Good morning. I'm R. Akshaya. I'm from CSIT branch. Today my Tech Talk concept is domain specific language for regular sets of strings and trees. Abstract. A new high level programming notation has been proposed called FIDO that we have designed to concisely express regular sets of strings or trees. In particular, it can be viewed as a domain specific language for the expression of finite state automata on large alphabets. FIDO is based on a combination of mathematical, logical, and programming language concepts. This combination shares no similarities with usual logic programming languages. FIDO compiles into finite states, string or tree automata, so there is no concept of runtime. It has already been applied to a variety of problems of considerable complexity and practical interest. In the present paper, we motivate the need for a language like FIDO and discuss our design and its implementation. Also, we briefly discuss design criteria for domain specific languages that we have learned from the work with FIDO. We show how recursive data types, unification, implicit coercions, and subtyping can be emerged with a variation of predicate logic called the monadic second order logic. On trees, FIDO is translated first into pure M2L via suitable encodings and finally into finite state automata through MONA tool. Introduction. Finite state problems are everywhere, embedded in many layers of software systems, but are often difficult to extract and solve computationally. This basic observation is the motivation for the work presented in this paper. Recent research has exploited the M2L on finite strings and trees to solve interesting and challenging problems. In each case, the results are obtained by identifying an inherent regularity in the problem domain, thus reducing the problem to questions of regular string or tree languages. Successful applications today include verification of concurrent systems, hardware verification, software engineering, and pointer verification. Work in progress involves a graphical user interface for regular expression extended with M2L and document logics for the www. The role of M2L in this approach is to provide an extraordinarily async notation for complicated regular sets. Applications have demonstrated that this notation is async can be used to describe properties where finite state automata, regular expressions, and grammars would be tend to cumbersome, voluminous, or removed from the user's intuition. This is hardly surprisingly since M2L is a variation on predicate logic, thus natural to use. Also, it is known to be non-elementarily more succinct than other notations mentioned above. Thus, some formulas in M2L describe regular sets for which the size of a corresponding DFA compared to the size of a formula is not bounded by any finite stack of exponentials. The flip side of this impressive successiveness is that M2L correspondingly has a non-elementary lower boundar on its decision procedure. Surprisingly, the MONA implementation of M2L can handle non-trivial formulas, some as large as 50,000 characters, 5 lakh characters. This is due to in part of the application of BDD techniques, specialized algorithms on finite state automata, and careful tuning of the implementation. The successful applications of M2L and MONA reside in a common productive niche. They require the specification of regular sets that are too complicated to describe by other means, but not so complicated as to be infeasible for our tools. Similarly to the early experiences with machine languages, we found that M2L programmers spent most of their time debugging cumbersome encodings. Here we can see the process of FIDO language summary. FIDO language summary. The four kind values: finite domains, recursive data values, positions in recursive data values, and subsets of such positions. We show that many common programming languages concepts to expressions. This semantic property allows us to view the compilation process as calculations on values that are deterministic. Finite state automata, just as an expression elevator, calculates on numbers to arrive at a result. This view is quite different from the method behind most state machine formalisms used in verification. A language resembling a general purpose language expresses a finite state machine, which state space and transition system is constructed piecemeal from calculations that explore the state space. Our, our view, however, is similar to some uses of regular expressions for text matching, except that most implemented algorithms avoid the construction of deterministic automata. In this article, we motivate and explain FIDO. In particular, we discuss the type system and comparison techniques. We also give several examples, some technical considerations concerning the relationship between our data structures for tree automata representation, and the comparison process will be explained elsewhere. Domain-specific languages. The design and implementation of a domain-specific language is potentially costly undertaking that must be well motivated, since there are clearly less expensive alternatives is using application-specific libraries or macro packages. In this section, we describe in more general terms the process that we went through to obtain the FIDO language. This process has been summarized. To avoid a wasteful and sterile project, it seems advisable to first gain significant practical experience with the application domain. If this reveals real software problems, then a domain-specific language may be the answer. The next step is then to perform a conceptual analysis of the application domain, distilling pure concepts that may be lifted to become language constructs. This process must also be guided by the known software problems which we seek to eliminate. M2L and Mona. Basic M2L has a very simple syntax and semantics. Formulas are interpreted on a binary tree labeled with one patterns determining the values of free variables. First order terms denote positions in trees and include first order variables and successors. Second order terms denote sets of positions and include second order variables, the empty set, unions, and intersections. The basic predicates are set members, equality, assenter relation, and set inclusion. The logic permits the usual connectivities and first and second order quantifiers. By convention, a leaf is a position P for which P is to 0 and P is to 1. The sublogic for the strings uses only 0 successor. Mona tool accepts such formulas in a suitable ASCII syntax and produces a minimum DFA that accepts all trees satisfying the given formula. Thus, satisficability of a formula is equivalent to non-emptiness of the derived automation. The motivation. A small example will motivate the need for a high-level notation. Assume that we wish to use Mona to prove the following theorem. For every string ABC and any is eventually followed by C, to state this theorem in M2L, we must first choose an encoding for the labels A, B, C. For this purpose, we introduce two free second-order variables x0 and x1. The labels can be encoded according to the following schema. A position P has label P and that is corresponds to a bit pattern 00. Similarly, we can assign to bit B a bit pattern of 01 and to the C pattern 1010. The property A is eventually followed by C becomes the formula. A reason for M2L specifications being such more voluminous than promised should now be apparent. Support for such encodings is usually supplied by a type system. We can see a syntax here like string x a plus b into c. For all POS, Px, p is equals to a implies that there exists POS q of x of p less than q and is equals to c. The keyword string and POS are intended to declare free variables of these two kinds. This formula can be read as for all positions p in the string x, if fp has label a, then there exists a position q also in x such that p is before q and q has label c. Arbitrary recursive data types may of course be expressed directly as follows, but the translation is voluminous and best performed automatically. The translation also solves the problem that the Mona discussion procedure works on formulas whose domain of discourse is only binary trees, whereas values in recursive data types are trees with a varying number of branches. Note that not all regular tree sets can be captured by recursive data types. Consider binary trees in which nodes are colored red, green, and blue. The subset of trees in which at most one node is colored blue is not a recursive data type. However, it is easily captured by the following FIDO specifications. The domain. While this paper is not intended as a proper language report, we will explain the more interesting or unusual concepts that the FIDO notation provides. Domains and data types. Finite domains are constructed from simple scalar lists freely combined with a product operator and a union operator. Then the union of two finite domains is formed. It is required as they are disjoint. If we define the domains as follows, we obtain values as A1, A2, B3, A2, B1 in formulas. Finite domain values may be defined using a syntax such as stage, where PC and R are unification variables. The finite domains could of course be encoded as data types. We have chosen to have a separate concept for several reasons. Variables. There are 4 kinds of variables in FIDO. We introduce them by examples. A domain variables S that ranges over states may be declared as tree variables X and Y as declared. Each variable defines its own space of positions. Quantification. All variables can be quantified over. For example, the formula there is a computational that contains a loop may involve quantification over both strings, finite domains and positions. Implementation. Here we have implemented a program of strings and trees giving a red, black and colors. Here here we are using macro operation. The null and WF predicates describe the relationship between a single node and its immediate descendants. The program follows. Formulas are included in this and the program follows again. And we have also discovered that the FIDO type structure contains a wealth of information that is not currently being exploited by the Mona implementation. Conclusion. In our opinion, FIDO is a compelling example of a domain-specific language as sketched in section 2. In this focused on a clearly defined and narrow domain. It uses a well-known and trusted technology, all the phases of a standard compiler including optimizations at all levels. Thank you.